In this chapter, we shall be looking at the properties of lipids, proteins, and biological membranes. Lipids are probably the most diverse among the different biomolecules that you will encounter. They're nonpolar biomolecules, insoluble in water, soluble in organic solvents such as chloroform or acetone, and they're quite diverse. They're found in many different parts of the cells or different organisms, egg yolks, the human nervous system, and very important component of plant, animal, and microbial membranes. In terms of biological functions, okay, the function of lipids are also quite diverse. Starting from the energy source, they have more than twice the amount of energy as carbohydrates. If you look at your energy label or nutrition label of the food that you eat, you'll see that 1 gram of fat provides about 9 kilocalories of energy, whereas the equivalent amount is only 4 kilocalories for carbohydrates. It's also an important role in energy storage. Okay, so the excess food that we eat, okay, is stored in our adipocytes as fats. Some of us are probably more familiar with it. Structural, as we will see later, lipids are very important components of our cell membranes and other biological membranes. Also, we will see some examples of lipids as hormones, specifically as prostaglandins and steroids. Later, we will also look at vitamins, the fat-soluble vitamins A, D, E, and K. And then other functions, they're also important in vitamin absorption. Okay, so the vitamins A, D, E, and K are lipid soluble. Therefore, we also require some lipids to allow us to absorb the vitamins A, D, E, and K from our diet. Protection. Okay? So if you've ever seen uh, food from the market, you'll see that there's usually a layer of fat around the vital organs. Insulation, okay, subcutaneous fat. Now let's look at fatty acids, one of the components of lipids. Acids are simply carboxylic acids with long unbranched hydrocarbon chains. So you've learned about this from your organic chemistry already. However, there's a general formula, okay, as shown, I will not mention it anymore, where N is between 10 and 22. So they are even numbers of carbons. And then from your organic chemistry, the hydrocarbon chain can be saturated. Hence, we have saturated fatty acids, just composed of carbon-carbon single bonds, or unsaturated, wherein there's at least one carbon-carbon double bond in the hydrocarbon chain. From the configuration for naturally occurring fatty acids is that they're cis. They can also be mono or polyunsaturated. So you may have seen this abbreviation MUFA and PUFA. Okay, so let's explore some of the structures of typical fatty acids. On the left is palmitic acid. Okay, so many different ways to represent the structure. Okay, so which one will you use? Again, we'll use the one that's probably most convenient, or it depends on what you want to emphasize as you are showing their structures. Okay, so palmitic acid, uh, we see has 16 carbon atoms in total, including the carboxylic acid. Stearic acid is carbon 18. Okay, so I think these are very, very common, fatty acids, I mean. Okay. Now, what about unsaturated fatty acids? Okay, so we have shown on the left oleic acid, which is 18 carbon atoms. Okay, and one unsaturation. For linoleic acid, it has two unsaturations. For linoleic acid, it has three, and arachidonic acid, it has four. Notice something peculiar about these unsaturations. They're not conjugated. And there's a way to represent the structures, okay, depending on the number of carbon atoms. If you look at the table 8.2, under the heading degree of unsaturation, we can abbreviate the structure of palmitoleic acid as 16 colon 1 delta 9. What does this mean? It means that there are 16 carbon atoms in total. There's one unsaturation, and the location of the unsaturation is at carbon 9. Okay, so recall your uh, organic chemistry on how to uh, indicate where the unsaturation is for a double bond in an alkene. It's the same way. Looking down, we see oleic acid, which is second on the list. Its way to denote it is as 18 colon 1 delta 9. So again, there's 18 carbon atoms. Location of the unsaturation is at position 9. Let's go to the polyunsaturated fatty acid, linoleic acid. It's 18 colon 2 delta 912. So if you're going to write the structure of the linoleic acid, okay, you're going to write a carbon chain of 18 carbons, okay, and then at position 9, there will be one unsaturation in the cis configuration, and then at carbon 12, there will be another unsaturation also at the cis configuration. Okay, so we have the line structure drawing over here, and we have the space filling model. And you can now extend what I just said to linolenic acid and arachidonic acid. Here's a table that I found from another source showing the properties of some natural occurring fatty acids and emphasizing their the derivations of their common names, the melting points, and other properties. Okay, so once again, the first column just showing the carbon skeleton. Okay, so for example, lauric acid is 12 dot 0, 12 colon 0, which means again it's just made of 12 carbon atoms, and and no unsaturations, and so on. So important thing to note, okay, to notice is the effect of the chain length to the melting point. But you already know this lesson already from your organic chemistry. Okay. So here's some interesting trivia on how the names have been derived. Lauric acid was derived from the laurel plant. Myristic acid from myristica, okay, which means nutmeg. Palmitic acid obtained from palm tree. Stearic acid, supposedly from the Greek word steer, which means hard fat. So if you've you've seen like fat from, say, the beef, the hard one, okay? So I guess that's how they derived it, okay? Arachidic acid from legumes, okay? Is that how you pronounce it? Lignoceric acid from lignum, which refers to wood, and so on. Okay, so now let's contrast the difference in melting points. Okay, so let's compare two fatty acids of the same chain length, but one is saturated and the other is unsaturated. So palmitic acid versus palmitoleic acid. Palmitic acid itself has a melting point of 63.1 degrees Celsius. Let's introduce one unsaturation and see the drastic effect in the melting point. This now melts at negative 0.5 degrees Celsius. So here, the important aspect is again the shape of the molecule and how it affects the melting point. So another set of comparisons for stearic acid, 18 carbon atoms, fully saturated, 69.6 degrees Celsius melting point. Introduce one unsaturation, drops down to 13.4. Another unsaturation, it's now -5, and another unsaturation, it's -11. So in this slide, we'll just look at the fatty acid composition of some common oils. We'll see now that coconut oil is about 48% fatty acid component. More on this later, no? Because the coconut oil does not really have lauric acid component itself, but it's part of the oil. For soybean oil, it's about linoleic acid is its greatest contributor. For canola oil, it's oleic acid. For palm oil, uh, it's actually almost equal between palmitic acid and oleic acid. So something interesting. This is just a reminder of the use of Greek letters. Okay, so the alpha carbon is the one that's next to the carboxylic acid group, and then beta is the next, and so on until you reach the end, and then the end may also be referred to as the omega carbon. Another interesting fatty acids are sometimes referred to as the omega-3 uh, fatty acids. They just have an unsaturation at the, it just refers to the third carbon at the end. And usually it has an unsaturation. So let's look at the physical properties of the fatty acids. Okay, one is a function of length. Okay, as you may have learned in your organic chemistry, okay, the longer the chain, the higher the melting point. Okay, and for carboxylic acids, okay, it's polar. So for short chain carboxylic acids, they can be soluble in water. Okay, actually the limit is about, I think, 6 carbon atoms, right? If you recall your organic chemistry. And then the longer the fatty acid chain length, the poorer the solubility in water. Typical fatty acids range from about 10 to 22 carbon atoms. So we'll see that fatty acids by themselves are mostly insoluble in water. Okay. And then the other one is, again, as mentioned, the longer the chain length, the higher the melting point of your fatty acid. And now we see some of the effects of the unsaturation. Oops, more on that later. We look at the effects of the unsaturation. Okay, so why is there a change in the melting point due to the presence of unsaturations? Okay, so if you look at saturated fatty acids, okay, they can line up pretty well with each other. So it's conducive to producing a packed structure. In the solid form, recall, our atoms, molecules, or whatever it is we are talking about, are uh, closely packed with each other, packed as closely to each other. However, if there's now some unsaturation, recall that the unsaturation, the cis unsaturation, usually has a cis configuration. So there's now a built-in kink, if you will. So they call this bend over here, referred to as a kink. So when you now try to pack fatty acid chains next to each other, they don't pack quite as well. So there's now a naturally distance, okay, formed between them. And because there's now distance between them, it's now easy for them to move around, or in other words, they become more fluid, okay, and then therefore it doesn't take much heat, okay, kinetic energy for them to be converted into the liquid state. So let's look at the reactions of fatty acids. You've learned this already from your organic chemistry, so this is just a review. Okay, so Carboxylic acid groups can undergo esterification. Okay, so you have carboxylic acid plus alcohol, and then you form the ester. It can also undergo acid-base reactions. Okay, so carboxylic acid plus the base, you form the carboxylate and water. The carbon-carbon double bonds, if you have unsaturations, can undergo hydrogenation. Okay, so you may have a catalyst, say platinum, palladium, or nickel. You just add the hydrogen across the double bond. So you go from unsaturated to saturated. So sometimes hydrogenation can be total or partial. With total, as the name implies, we completely hydrogenate all the unsaturation present in the molecule. In partial hydrogenation, as the name implies, you don't fully hydrogenate all of the unsaturations in your molecule. So it may just be one or the other that is hydrogenated. Okay, so in the product, it will be a mixture of fully hydrogenated and hydrogenated products. Yung spelling. Okay. Now, just like amino acids, we have common amino acids and uncommon amino acids. So would it be also for the fatty acids? There are the unusual fatty acids. Where can they be found? They can be found in the membrane of various bacteria. For example, the propane ring, okay, can be found in lactobacillic acid. It's bacteria that cause leprosy and tuberculosis, and in some virulent bacteria. They can also have some branch chains. Okay, so for example, in the tuberculosteric acid. There can be other modifications, such as addition of hydroxyl groups. Okay, if there's hydroxyl groups, reminder from your organic chemistry, they can be oxidized into the ketone group, okay, or even epoxides or methoxy groups.